Okay, and we're good. So we stopped in the middle of something last time. Let's just jump right back into it. We were factoring trinomials, or more specifically, second degree polynomials. I believe our last example was we wanted to factor the 2x squared plus 5x plus 2. It's factored using the AC method. I want us to look at another method, the other one. I don't know what it's called, I just call it trial and error because it's kind of like a trial and error. A lot of people know the AC method, and if you don't know the AC method, I actually wrote down the steps. It's very somewhat straightforward, I would say. So now I'm going to kind of teach you how to factor these guys kind of by eyeing them and just taking advantage of certain patterns. And ultimately, if you get really good at this, you'll do it a lot quicker than the AC method in general. You can get actually really good at doing this. So I'm going to actually describe to you how you would actually accomplish that. First of all is you want to notice a certain pattern. Let's say if I wanted to expand two things. You can apply the distributive law and expand those. You would get dx times this guy, you get dfx squared, plus you would get dgx plus efx plus eg. And you would be able to simplify that. You get dfx squared plus dg plus ef times the x plus the e times the g. And here's the pattern I want you to notice, is that didn't buy these colored chalks for nothing. If you look at the first coefficient of x here, you can notice where that came from. That is the product of the two first terms. And if you notice where the last guy comes from, blue, that is the product of the two last terms. Right? So if you take dx times fx, you would get dfx squared by laws of exponents. And if you take e times g, you get e times z. That's the last guy. But what happens to the middle guy? You'll notice that when we kind of combine like terms here, this middle term, the middle coefficient, it actually came from doing what? If you actually take the two outer terms, right? So this is outer. And you add it to the two inner terms. So here's the inner. And you actually add these together. That is what actually gives you the middle term. So now you can take advantage of that pattern, knowing that something like this can factor to something like this. And in particular, if this d times f is not 1, it's some other number, we can kind of know how to break things up and see when this pattern is taking effect There's nothing really to say else about how the method actually works. And this is why it's kind of trial and error. You're just going to try to plug in numbers to get this kind of relationship to happen. Let's actually do it again. Let's do this guy just by taking advantage of this without actually worrying about the AC method per se. So here's how you go. And I'm going to do it incorrectly like the first time, just so you can see if it goes wrong, what's going wrong, and how you can actually fix it. But let's actually just jump in. So let's see how we are going to do this. So we can right away just throw down our parentheses here. Okay. Now, here's the thing. We need to put two terms here in the front so that when those guys multiply, it gives us the first term, because that is the pattern. Now, when your coefficient is a prime number, that's actually pretty easy, because 2 is prime. Not many numbers other than no integers other than itself and 1 are the only positive integers that divide into 2. So pretty much to get to that 2x squared, there's only one way. It has to be a 2x and a 1x, right? So you actually break up a product into that 2. Now if this were like a 6, you'd have options. There could be a 6 and a 1 or a 3 and a 2, but for 2 it's easy. So you're going to just break this up like that, so that when these guys multiply back out, you get the first term. Now what you want to do is you want to put in the guys of the last part to get the last term, which is what we're going to do. So now again, I want to come up with two numbers that multiply to give me 2, which I'm going to put in this location. Now, again, in this case, it's a very easy example just to ease into it. There's only one option really, 1 and 2. But now you might say, well, where does the 2 and the 1 actually go, right? So let's say you first put the 2 here and the 1 here, which would actually be incorrect. Okay, so look at that. I know to get the first term, it has to be the product of the two first terms. There's only one way to break down 2 into 2 and 1, so it has to be 2x and 1x. Okay, we're awesome. Look for the what product of two things that will get me the last term. Okay, 2 and 1 again are easy. Now what matters is what order and what signs they take. So how do you actually know that this was wrong? Well, if I were to multiply these two, I would get 2x, right? If I were to multiply these two, I would get 2x. And now I ask myself, can I, using 2 and 2 with addition or subtraction, get to 5? And the answer is no, that's not going to work, right? So I know that order is actually wrong. This is actually not going to work because the pattern for the middle term doesn't actually work out. Here's another way you can notice that this wouldn't have worked out. If you put the 2 here, you notice there's also a 2 here, which makes 2 a common term, which means I could factor out the 2. Which means that 2 is going to be here multiplying this whole thing, which means that 2 should be a GCF of the whole thing. But if you look up here, 2 is not a GCF of the whole thing. I can't get that 2 out of 5. So the fact that putting the 2 here is going to create a GCF, which I know isn't there, is one hint to me that something is off. And the more important hint is that, yeah, if I multiply these two and multiply those two, I can't get them to add or subtract to get that middle one. So what you do then is you would swap it. You put the 1 here and the 2 here. Now if you look at that, what's going to happen? Well, if I multiply these two, I would now get 4x. If I multiply these two, I get 1x. Could I get to a positive 5 with a 4x and a 1x? Sure. Just make both of them positive. So make this a plus 1 and a plus 2, and we're done. Now, all that happens in your head, and the more you practice it, that'll all happen in like a few seconds. I know you might not believe that if you've never seen this before, you're not really used to this method, but trust me, you take an afternoon and practice this, and you'll get so lightning fast at it, you can wow all your friends and all kinds of stuff. So, yeah, that's what I call trial and error. So what I want to do is I want to factor a bunch more things using this method, because Most of the time, if in class I'm doing some example of something, I'm not going to go to the side and do the AC method. I'm going to just factor it on the spot because, that's more efficient that way. So, just to get you guys used to doing it and used to actually seeing me do it, let's actually do some more examples where we're going to factor using this idea. So the instructions are to the back. Let's work through those. And I guess if you have any questions about this, they'll come up as we're working through these. We're gonna jump right in. All right, what do we want to do here? Let's take a guess. What do you want the first numbers to be? 3 and 2. Sounds great to me. Let's do that. What do you want the last numbers to be? Well, 2 and 1. Where do you want to put the 2?
In the first one.
Kind of makes sense to put it here because if it's here, 2 is a common term, which it's not for the middle term. So that would make sense. If this arrangement is going to work, that's going to be the way to get it to work. Now, the middle term gives you 4x. The last term gives you 3x. Can I get to a 1x from a 4x and a 3x? Well, sure. Make it a plus 4 and a minus 3, which means I need a negative sign here and a plus sign there. That's it. Oh, look at that. Our first try. Like, we didn't even have to get anything wrong. That's the factor. Which is a lot nicer and quicker than a AC method and then splitting the middle term and factor by grouping and pulling out. You can just kind of throw them in. And you kind of know that the 2 and the 1 have to go here, like I said, for the reason of the GCF. But let's say you put the 2 and the 1 here and this still didn't work out. That's going to hint you, yeah, I probably should have used 6 and 1 instead of 3 and 2. Or maybe swap the 3 and 2. And you just keep moving things around. A lot of it would be in your head. By you just trying to get these middle numbers, because you're always only putting numbers in the first term and the last term that's going to produce the first term and the last term. So you don't have to worry about those. You just keep moving things around until multiplying these two and multiplying those two can add to give you the middle, right? So and you're just rearranging them to obtain that. Go, open these up. What do you think can work for the first numbers? Huh? 5 and 1. 5 is prime, so it's only 5 and 1. And 3 is also prime, so it's only 3 and 1. Where do you want to put the 3 and the 1? 3 here, 1 here? Okay, well what if I felt like doing that? Okay, so then I would say, oh, that's a 5x here. Then that's a 3x there. Can I get 14 from 5 and 3? No way. Okay, so that doesn't work. And then the 1 here and the 3 here. Well, that's 15. That's 1. Can I get a minus 14 from a 15 and a 1? Sure, make it a minus 15 and a positive 1. And this will be a minus to get the minus 15. This will be a plus to get the positive 1x. There's nothing really to write down. The process kind of happens in your head. Yes.
I just have a question. Like, is there ever a time when the AC method like wouldn't work and you'd have to use this, or
No.
you could just use AC every time?
Yeah, you can use AC all the time if you want.
Alright.
As long as it can factor, the AC method or this will actually get you there. If it doesn't factor, which we'll talk about situations like that later on, you might have to use quadratic formula or something like that. And the quadratic formula works in all cases. But as you'll see, and I think we'll get to some examples today, sometimes factoring isn't the main goal. You're factoring on your way to doing something else. So you don't really want to spend a lot of time on the factoring part. You want to get it over with so you can get on to solving the rest of the problem. So the quicker you can actually learn to factor something, the better. So I wouldn't really recommend just taking the easy way out and say, well, I already know the AC method, I'm going to just forget about this and just always do the AC method. You're costing yourself time by making that decision. It's worth a shot, and I'm telling you, you'll actually catch on to it pretty quickly, quicker than you'd realize. I have a funny story about that. I'll probably tell you guys. I have lots of stories. Okay, let's do more practice on this. Okay, go. Okay, guess it. Just throw them out. It doesn't matter if they're right or wrong.
3x.
3 and 4?
Yeah.
Okay, let's go with 3 and 4. Okay, the 6.
2 and 3.
Where do you want to throw
2
it?
on left.
Two were first.
So you have 2 on the first one.
And three in the middle.
No.
Two.
Yeah, think that'll work out? Does that work?
Yes.
Because this gives us what? 9 and 8? Yeah, those add up to 17. And that is factored. Okay, what about this one? How do you factor that? Yeah.
3 parentheses x plus y on one side. 2 on the other, 2 parentheses x plus y. -1, -3.
-1 here and -3 here. Well, let's see. This will add up to a -2 blah, and this will add up to a -9 blah. That gives us -11 blah. Yeah, that works. So, I mean, you could actually write this out a little bit. I mean, this one is not really worth it. Like, if there was a number inside here, I'd probably write it out a little bit more. But this is like 3x plus 3y minus 1 times 2x plus 2y equals 3. Okay. Look at that. I'm not gonna change anything, everything's fine. I'm just gonna, okay, so I want everyone to do this, and I'm gonna do it on a timer. So I'm going to give you guys like 10 seconds. Go! Go, now! Okay, we're at 15, come on.
Oh, snap. Oh, okay.
Who finished it? Did anyone finish it? Okay. Okay, that's 40 seconds. That's forever. Okay, let's, you guys need to, I think you guys just got freaked out when I said, I'm gonna time it, oh my god! But that's, gotta learn to handle the pressure. That's, a lot of school is about pressure. Yeah. Okay, let's think through okay, so what do you want to do here for the first part?
2x squared.
2x squared,
X squared.
x squared. Yeah? Last ones?
3, 1.
Yeah, 3 and 1 is the only one, and again, 2 is not a common term, so it doesn't make sense for the 2 to be here, 2 to be here, and 2 to be here, and 3. What would we have here? See here?
It's the other way. So, no, 3.
Yes.
3 on
This would give us 6. That would give us 1. You can't get to 1.
3. It's 3.
So put the 3 here, and the 1 here. This would give us 2. That would give us 3. How do the signs work?
Plus 3. Plus 3.
You need a minus 3 and a plus 1. Because you have the minus 3x squared plus the 2x squared gives me the minus 1x squared. Now technically this can factor further if you want to use radicals, but let's actually leave it in whole number form. And that's that. So I know this kid, when I was a kid, this is little Jhevon. I don't know, I was like 8 or 9 years old, something like that. And we were doing factoring in math class. And I had a lot of trouble with it. I was struggling with it. Not just this, it included this, but like factoring in general, like big factoring stuff. We covered a factoring unit, and we just had to factor all these things crazy fast like that. You'd be like, ooh, 10 minutes to do 20 problems, and everybody's like, ah! Yeah, anyway, I sucked, okay? So, I went to my dad, hey dad, I'm having trouble with factoring, you know? He's like, oh, okay, so let me show you. You know, he showed me how to factor things, showed me all the tips and the tricks, and you know, I only knew the AC method. He showed me this thing. Oh, you just check that these two and those two, you have them together. Really? Why did you tell me? Right. So he explained all that, and then he got up and he asked me, "You get it? You get it?" I'm like, "Yeah, I think I got it." And then, okay. Then he got up and he went into the other room. I didn't know where he went. He came back because we had a little library and stuff. He came back with like 5 textbooks, I think. He's like, these are all the algebra textbooks I could find. He drops them on the table and he's like, find every factor and problem in those books and do them. Show me on Monday, because my class was on Tuesday. Show me on Monday. Okay, so where I'm from, corporal punishment isn't considered child abuse. So, you know, if you don't do what your parents say, there are consequences. You get what I'm saying? Like when your father tells you to do something, do all the factoring problems in these books. You do all the factoring problems in those books. You understand? Because no one's going to stop him from murdering you for not doing that. Okay, so I remember this because that weekend my cousin was having her birthday party and stuff like that, and you know, my cousin always had the best birthday parties, you know, laser tag and bouncing castle. Yeah, so everyone was running around having fun. I was at the table factoring.
That's for sure.
Eating cake with one hand, factoring with the other hand. At the end of that weekend, I got like, it was like 400, 500 factoring problems that I got through from all those books. Show my father, okay, I think everything is right. Yes, I checked the odd ones and I multiplied out and manually checked all the even problems. And yeah, so, okay, good job. And that was it. And then he walked away. Next day I went to school. Teacher says, all right, we're gonna factor some stuff. Everybody shut up, sit down, be quiet. Throw down like 15 problems on the board. All right, everyone shut up and factor these. I'll give you guys 15 minutes. You better be done or else, you know, the teachers used to have like a ruler. Like it's a thing. Okay. Like everyone hits you when you're a kid. It doesn't matter. Okay. So, and if some adult hits you for misbehaving, they tell your parents say, good job, thank you. Like, they don't like, why did you hit my kid? That's not a thing. Yeah, so like everyone hits you when you're back. Okay. So yeah, she did that. And like, oh man, more factoring. This time I was sick of it. I was like, oh, okay. But the teacher started walking around the room. So You know, so I'm like I'm afraid of, you know, I don't know if she saw me roll my eyes because I don't want an adult to see you roll your eyes at them. So I'm freaking out and say, okay, fine, I'm gonna just get it through. Right? You know, she walks in, she looks at my thing, and she's like, she walks away. I'm like, oh crap, what did I do? And I looked at my paper and it was like, I was copying down the wrong things. Like this wasn't even what she wrote on the board. But then when I looked closer, I realized I was writing down the answers. I got so good at factoring. I looked at the board. By the time I looked down at the paper, my brain figured out the answer and I wrote down the answer without even thinking about it. That's what doing 400 factored problems does. Now, 3 days prior to that, I sucked at factoring. So I'm telling you, you can practice this and you can get good at it. You can get good to the, you would amaze yourself how good you are. Like I thought, am I the god of factoring now? Or like, did I get bitten by a radioactive spell? What happened? No, it was just I did 400 factoring problems. And I manually checked them. I did all that, just really just hammered away at it for 72 hours. Came out on the other side, I could factor things by looking at them. Oh yeah, I can write down the answer. Right? Even today I'm not that good at factoring because I've fallen out of practice, but back then, I was like, 10-year-old Jhevon with factoring, are you kidding me? It's awesome. So yeah, so sometimes you'll see certain things in math where it's like, can I just do it this other way I already know, but the new way that they're kind of teaching me is more efficient? Sometimes just bite the bullet and learn it. And it might feel unnatural to you at the beginning, but you drill it. Trust me, you'll adapt. And yeah, that's my little factoring story. Let's move on to some special factorings. These are using the things like difference of squares, sum and difference of cubes, the formulas that I asked you to regurgitate on your quiz today. So it's just using those formulas. So we have the, so I don't know if I want to do all of these as I'm working on this. So we have difference of squares. So that's the thing that says a squared minus b squared. If you see something like that, anything that looks like this, it factors into a minus b times a plus. Okay. And the a and the b can be anything. And as long as, and we even used this last time in the thing I had over here, where we had 2x to the fourth minus x squared minus 3. This will also work if you are proportional to 2. So if you have a to the 6th minus b to the 6th, it can factor like this. If you have a to the 4th minus b to the 4th, it can factor like that. That also would be useful in the bonus of the quiz, and things of that sort. So this you want to think of, again, as a general template. It's kind of like, this is the form of a dog. Anything that remotely looks like this is a dog. It's the same thing. Once the powers are even and they're being subtracted, you can do this. Okay? But this is the basic, the quintessential example. So nothing much by way of theory to go here, so let's actually just jump to some examples. So factor, some of these are kind of silly. X squared minus 16. I'm going to skip some of these, forget it. 25 minus 36. So all of these will be a lot easier by you remembering the difference of squares idea. And we'll get through the sum or difference of cubes idea, and I think we'll do a general strategy after that. Okay, x squared minus 16, what's that? So that's just you realizing that this is x squared minus 4 squared. So anytime you can write anything as a square, or a difference of squares more specifically, you just put the first thing minus the last thing, which is here the things are x and the 4, and then the first thing plus the last thing. The order doesn't matter, it's multiplication, but yeah, that's it. What about 25x squared minus 36?
5x.
Minus 6 and 5x plus 6. Okay? And that's by realizing that this is really 5x all squared minus 6 squared. And then the 5x is like the a and the 6 is like the b. So it collapses very nicely into that. See. What does that factor into?
X plus, and then 4 and 5. And then x minus 4.
Because you realize that this looks like x squared minus 4 over 5 squared. So that's like the a is the x and the b is the 4 over 5. A minus b times a plus b. Examples go on and on and on. Let's look at this one. Get a little crowded over here. Gonna try to have to erase this right away. Okay, this one.
2x cubed minus 3y squared. And then 2x cubed plus, yeah.
Right. This is for me recognizing this is 2x cubed to the square. This 2 squared is 4. And if I take x cubed squared, I get x to the 6. So you need, of course, you need the laws of exponents here. And this is 3y squared squared. 3 squared is 9, y squared squared is y to the 4th. And so this is really the difference of squares. Right? Now, like I said, it might not jump out at you that it's the difference of squares right away, but if that's the case, you don't know the difference of squares formula well enough to actually see it imprinted on something. And it turns out whenever there's two terms, you will tend to think difference of squares. Although there are other scenarios where difference of squares will pop up even though originally they're not two terms, like examples F and G. Okay, so want to factor this?
Isn't it like x minus 2 parentheses,
Mm-hmm.
plus 4, and parentheses x minus 2 minus 4.
Alright, here we could say this is x plus 2 times x minus 6. Did you figure out x? Is that why you said O?
Yeah.
Okay. How do you do it?
Me?
Yes.
Oh, okay, so the first three terms group together to form x minus 5 squared.
Alright, factor this, you get x, if we do it the the long way. I did give you the form for expanding a binomial, but you could even factor this the short way. You realize 5 and 5 would be the guys you would pick, and minus and minus would work. So this whole thing is actually x minus 5 squared minus y squared. And then this is difference of squares. So it's x minus 5 minus y times x minus 5 plus 4. There was a problem in my differential equations class the other day, and this is a class that you take around, it's kind of on the same level as calculus 4, but it's kind of easier than calculus 4, whatever. Students usually take it at the same time. Calculus 3 is a prerequisite for this class. And there was this problem that like kids couldn't figure out, and then I had to tell them, dude, it's difference of squares. But it was a problem kind of like that. They had to kind of see it. And if they didn't see it, it took them forever to solve it. And if they saw it, it was like, oh, what? It's like two lines. So yeah, this thing, it's something that you will continually need to always be looking for. Forever, much beyond this class. As long as you're doing math, you're going to want to know how to factor things, and you're going to want to know the special factor, because it's always going to be relevant. Here, we see 4 terms, so we're thinking factor by grouping. At least that's what we should be thinking. I'll talk about that in a little bit. Common term here.
Square.
Common term here.
-9.
So now x plus 2 is a common term. And that's not done. We can factor further, right? Because this guy is a difference of squares. 9 is 3 squared. And that is fully factored. Yeah, for these, not a bunch of theories, just you taking advantage of the pattern given by the formula. Another pattern that you should be aware of is the sum and difference of cubes. So that's the thing that says, well, if you're adding 2 cubes, then that's going to be a plus b times a squared minus ab plus b squared. And if you're subtracting 2 cubes, that's a minus b times a squared plus ab plus b squared. Common error here is students writing a 2 in front of the ab because they remember that a minus b all squared is the 2. It doesn't have a 2. Some examples. And again, factor. Turns out you can factor x cubed plus 8. You can also factor a cubed minus 1 over 27. You can also factor something like x to the 6 minus y to the 6. We're going to run through these because I want to make sure that I don't run out of time for the actual wrap-up today. Because in terms of factoring, we've actually learned most of the techniques that we're using. Even when we're not looking at things that look like polynomials, the kind of lessons and the skills that we learn by looking at things like this can often apply to other kinds of functions. And we'll see that throughout the towards the end of the course, when we kind of start looking at other things like trig functions and stuff like that. You're going to realize every now and then, like knowing how to factor a difference of squares is going to help you to solve a trig equation, things of that sort. So, like learn our lessons from things that look like polynomials or almost polynomials. Well, these are all polynomials. We can apply these lessons in more generally to other things. What do you think about the x cubed plus 8?
You can change that.
Alright, this is x cubed plus 2 cubed. So what did that look like? X plus 2. I'm just taking the x like the a and the 2 like the b. So I have the x plus 2, x squared minus 2 times the x plus the 2 squared. So that actually factors. This part will usually not factor any further, so let's not worry about that. That would be the answer. The quadratic part doesn't really factor more generally. Otherwise, we would have written it out in the form. Like this is usually the extent to which you're going to factor something. A cubed minus 1 over 27. You need to factor that. This might look a bit daunting, but if you realize that 1 over 27 is 1 cubed, 1/3 cubed, then it's just a matter of applying this formula where that's the a and that's the b. So a minus 1/3 times a squared plus a times b. So this is 1/3 a. Plus the b squared, 1/9. And you can verify in your own time that if you multiply this out and expanding everything and cancel like terms, you'll actually end up with that again. Now this is a nice example because it really illustrates a nice lesson here. Anyway, how would you guys do that?
X squared plus 7 minus y squared.
And then?
I factored it before, but it's x squared minus 4 and then x plus x squared plus 1
This can factor further.
plus y.
And you know what? This can actually factor further. So herein is the lesson. Now, yes, I'm going to do an example where I actually factor this guy even further. But right now, as you can see it, you probably can't think of a way of factoring that further. But it turns out that there's a bigger factoring here. You can factor it so that you decrease the powers even smaller, and you can get an extra factor out of this. Now, here's how. And here it is a part of the lesson. In difference of squares first. In other words, I would first think of this as x cubed squared minus y cubed squared. Then I would apply the difference of squares. And now each of these I can factor. So the first one I'm going to apply the difference of cubes formula. X minus y times x squared plus xy plus y squared. And then this one is going to be x plus y times x squared minus xy plus y squared. And of course, these two guys here are those two guys here. And what are those two guys? Well, they have to actually be this guy here, right? They're the same number. Okay? So here's kind of a tip And it's not just for fractions, this is kind of something in general. When several techniques apply, not all cases, but very usually, it tends to be better, nicer to apply the simpler technique first, right? Cubes is more complicated than squares. Go in and deal with the squares first, then deal with the cubes, would be the lesson here, right? Because when you look at this, you can see, well, I can think of that either as a difference of squares or as a difference of cubes. Chances are going with the squares first is going to end up to put you in a nicer position. Try to apply the easier technique first, and as referenced here. Another way in which this is kind of another take on this, it's kind of different, but it's kind of the same idea as well. PEMDAS works from the inside out, but when you're trying to figure out how you want to actually approach a problem, you tend to want to look from the outside in. You tend to want to look at the macro level, what's going on, before you look at the micro level. So figure out any global patterns before getting lost in the minute details, because those are more complicated to deal with. Is minute spelled the same way as minutes?
Yeah.
Damn the English language. Okay, so what I mean by that is, say, something like this. If I were to ask you to solve an equation like this, most people would start worrying about, oh, I don't remember about how trig functions work. But you see, if that's the first thing you notice, that the trig function is there, you're probably looking at the problem the wrong way. As a whole, what's going on here? What is this kind of object?
What?
As a whole, if I were to look at this whole equation as like one big thing, what is the pattern? Yeah, it's something squared minus 2 times the something plus 1 equals 0. Now what kind of equation is that? There's a name for it, you guys know? Quadratic?
Yeah.
Right? So you see a problem like that, you want to notice it's a quadratic before you notice there are trig functions. You kind of get what I'm saying? Because that's going to actually give you a much nicer approach. Deal with the easier, global, simpler idea first. A lot of times you start to break that down, it makes you dealing with the actual details, the specifics, like, oh, there's specifically a sine function here. It makes dealing with that easier in the long run. And that's in every class. Until you start getting to like, serious math classes where you have to like prove stuff, and then that might change. But as long as you're doing computational algebraic stuff, chances are noticing patterns on the whole first, or noticing the simplest technique first, is going to actually make your life work out easier. And yeah, it's just nice. So, those are just some side notes I wanted to mention. To wrap up the section on factoring, because we've done pretty much all the techniques I wanted to do on factoring. The next time we meet, we'll do a completely different section, where again we're looking at different things but applying some concepts that we have actually learned earlier. I want to tell you about a general approach to factoring. Right? Now this is one of the things you guys should be paying attention to. Like in the last talk I had with you guys, I mentioned that knowing about strategies and patterns and algorithms is a very important thing to know. So when you want to factor this random thing, you should have in your head an idea or a plan of attack how you're going to factor it. So how to factor anything. If I give you a problem, this has to say factor. There are certain things that you look for, and there are certain things that you'll do first as opposed to second. There's some general, the thing you do first is look for a GCF. If there is one, factor it out. Doesn't matter what it looks like. If you know the goal is to factor something, the first thing you should look for is the GCF. It's always the first thing you want to look for. The other ones are kind of depending on the situation. If there are two terms, you're going to want to think one of these things. Difference of squares. Try to see if that's going to apply. Can I think of the powers as being even? Or some difference of cubes. Now yes, there are difference of fourth powers and sixth powers, and you can go higher. But in a class like this, I'm never going to ask you to go beyond difference of squares or difference of cubes. 3. If 3 terms are the thing you're looking for, and again, GCF is always the first, but once you've factored out the GCF, then if there are 2 terms left over or 3 terms left over, you're going to think the same. Think AC method or trial and error. And trial and error is recommended. I'm not going to force you to do something you're not comfortable with, but if you can get comfortable with trial and error, I would recommend going that route. Yeah, or just how to factor trinomials, which we started last class. If there are 4 terms. Think grouping. Of course, factor by grouping means you need an even number of terms because you want to have the same thing left over in the parentheses at the end. So at the very least, they have to be the same number of things in each parentheses. So if you see 4 terms or 6 terms or 8 terms or etc., you factor by grouping might be something that can work. The 5th thing, you always check to see once you apply a rule, you're again going to look at it and check, can another rule apply? So this applied earlier, I believe, when we had this problem. 18. Yeah, we started out with grouping. This was a square. We started out with grouping, but then after applying grouping, we realized that we were left over with a component that could be factored further, that went further. So once you apply one of these rules, you're going to want to check, can I apply something again? Is everything broken down as far as it can break down? But you always think GCF first. If there are 2 terms, you're always going to be thinking difference of cubes, difference of squares. Probably difference of squares should be thought of first. And if both apply the difference of squares first. If there are 3 terms, you want to think trinomials, AC method, trial and error. 4 terms, you think factor by grouping or any even number of terms like 6 or more. And then check that if you can go actually further once you've actually applied a technique. that's kind of what you want to go through with each factor. That ends today's. I'll see you guys on Thursday.